Thank you for waiting. Now, Mr. Mikito Hasegawa, if you please.
Thank you very much for inviting me to give a talk today. I'm Mikito Hasegawa, the network planner of SEIKO Solutions, Inc. I'm afraid my expressions may be rude or hard to listen because I'm not so good at English. Please be patient. Today, I'd like to focus on the time synchronization. There are 2 points in my presentation. So one is the popular protocol NTP. NTP means Network Time Protocol. I'd like to talk about NTP leap second in this July. Another is PTP. It means Precision Time Protocol. PTP is another network time synchronization protocol, which is more accurate in time synchronization than NTP. First, I talk about NTP. A large number of equipment has a function of NTP client, PC, server, router, surveillance camera, copy machine, etc. So NTP enables the equipment adopting network to synchronize time accurate. Recently, various systems are synchronized by using NTP. I guess Rakuten market also use NTP to synchronize equipment, right? One of the most important problems of NTP's time synchronization is so-called leap second. Leap second is a 1 second adjustment that is applied to coordinate universal time, UTC, in order to keep accurate time. Without leap second, UTC time is deviated from atomic time as a result of Earth's rotation. The latest leap second occurred on July 1st, 2015, at which 1 second has been inserted. NTP's leap second can be proposed by setting leap indicator. Recent leap second is inserted with 1 second, so the leap indicator is set at 01. Clients are required to recognize the code of leap indicator 01. However, there was an instance in which a client adopting particular version of Linux stopped its service due to CPU utilization program. For example, even when the clients inputted the leap indicator 01, their servers failed to misconnect the leap second. They counted 59 seconds twice, but not inputted 60 seconds. If clients do not fully prepare for the leap second, they may face such problems. There are 2 solutions to operate leap second on NTP server. One is to insert leap indicator 01. This solution is a standard method that confirms RFC of NTP, but clients need to recognize leap indicator exactly. Another solution is to adjust 1 second gradually. This is SEIKO original adjust mode. The adjust mode allows adjusting 1 second gradually while keeping leap indicator at 00 in the NTP packet. This solution enables insertion of 1 second without awareness of leap second by the NTP client. NTP clients can synchronize NTP servers by through modes so you can avoid setting or problems about Linux. As I mentioned at the beginning, NTP clients are equipped at variety of machines. So it is hard to grasp every client's leap-second operation. Thus, we provided the adjust mode for time synchronization. I briefly explained the role of NTP in leap seconds. Here, I introduce PTP, Precision Time Protocol, which enables more accurate time synchronization in compared with NTP. Whereas NTP has millisecond accuracy, PTP provides nanoseconds accuracy. I summarize the protocol of PTP and results of the connection demonstration between PTP servers and the computers at SHONET in the exhibition interlock held in this June. As a member of SHONET NOC, I conducted the PTP experiments with the help of Associate Professor Dr. Sekia. Agenda. What's SHONET, methods and challenges for obtaining the highly accurate time, problem solving approach, what's PTP, PTP interoperability testing IoT, results of PTP IoT, summary. First, I explain what the SHONET is. SHONET is a versatile event network constructed for Interloop Tokyo, which includes interoperability experiments of latest technologies, demonstrations, and internet access services for exhibitors. Technicals are challenged to spread among industrial in the near future. New products of debut at home and abroad. And only Interloop Tokyo succeeds the original spirit. It is built with the Trinity consists of NOC team members gathered from industries, academia, and government. Contributors providing equipment and services, and STM volunteers invited from the public. I joined to SHONET as a NOC member, and SEIKO did so as a contributor providing the equipment. The demonstration of PTP connection was conducted as a part of networks like that. So how can we achieve the nanoscale accuracy? A key method is to use Global Navigation Satellite System, GNSS, also known as GPS, which provides the source of accurate time. It needs GNSS antenna in order to receive the time source from GNSS. Time-receiving devices and antennas are connected with a coaxial cable. However, it is hard to construct GNSS antenna in some cases. In most cases, a large scale of construction will be required, and this needs costs. It has been used to set the antenna for each device to obtain accurate time from GNSS. Increasing the amount of demands that require accurate time synchronization makes it difficult to set an antenna for every device. Especially equipment for the small base station are widely developed according to the spread of mobile LTE advanced. So far, allocation of the macro cell, which covers the wide communication area of a radius of several kilometers. In the future, allocation of the microcells, picocell, femtocell, which covers a small communication area of a radius of from 10 meters to several hundred meters. The location of microcell is almost in basement of large-scale commercial facility, so it puts larger costs. So it is not realistic to set the antenna every device due to cost problems. As you can see, mobile technology requires highly accurate time synchronization, LT advanced. So the most problem is in case of allocating the same number of GNSS antenna as the equipment. As the devices increase, the exclusive antenna and installation of coaxial cable are required. It results in increase of costs. And here we offer two solutions to obtain highly accurate time synchronization. Number one, use of GNSS coaxial distributor. Number two, use of PTP precision time protocol. Using GNSS coaxial distributor is not flexible, so PTP would be a fascinating protocol to achieve highly accurate time synchronization. In addition to the mobile technology I introduced, PTP can be applied to the next generation broadcasting, such as 8K and hybrid cast. And Tokyo Stock Exchange Inc. has started to apply the PTP connective service. So let me finish the introduction of PTP. Now I will explain what PTP is. PTP is precision time protocol, which is regulated by IEEE 1588. Whereas NTP has millisecond accuracy, PTP has nanosecond accuracy. Why the PTP is more accurate than the NTP? It eliminates the effect transmission delay, which is the main cause of errors. It is recommended that time when the packet passes the physical layer should be stamped. And the more packets sent and received, the more accurate the statistics information. If adopted to mobile technology, it allows transmitting a maximum of 128 packets per second. So I will show you clock types defined by PTP. There are three types. Ordinary clock, OC, has a single port activated in PTP domain, correspondent to slave, which synchronizes with grandmaster clock, ZM, distributing time or the time distributed by ZM. And boundary clock, BC, is allocated between ZM and slave. BC synchronizes with the time distributed by ZM. BC itself distributes the time based on ZM to slaves as a ZM. And transparent clock TC is allocated between ZM and slave, like BC acts differently. And TC writes its internal delay information into PTP packets, and therefore slaves are able to detect the internal delay of TC. It makes possible to keep the accuracy of PTP packets distributed by ZM. Boundary clock and transparent clock are mainly supported by switches and routers. So as I told you before, PTP is precision time protocol, which is regulated by IEEE 1588. IEEE 1588 has been called as a default profile, but is now changing to profiles that are specific to a particular demand. Mobile technology field demand telecom profile. So next is about interoperability demonstration experiments. Application of PTP for various industries assuming the acceleration of multi-vendor of the PTP network. We demonstrated interoperability tests between Grandmaster Clock, slave products, and major network products, boundary clock. We also carried out the interoperability tests between default profiles and telecom profiles, both of which are commonly used in devices. Profile supports for the devices provided in ShowNet are as follows. Since it was unclear the interoperability between different types of profiles, we tested this using different equipments. Next is configuration of PTP. Grandmaster Clock was prepared to provide highly accurate time to devices through GNSS antenna set at the rooftop of Macquarie Messe. Config 1 is a simple configuration just to confirm the interoperability of Grandmaster Clock, boundary clock, and slave. As it is the first case of PTP test in ShowNet, we have to grasp the level of the interoperability. First of all, tests were carried out between equipment supporting default profile and telecom profile in this configuration. Config 2 and the configuration in which boundary clocks are allocated in multi-layer between Grandmaster Clock and slave. When configured PTP networks, this configuration is considered simplest. SEIKO provided two Grandmaster Clock. One supports default profile and the other supports telecom profile. Continued from the previous page, config 2 configured for default profile and telecom profile separately. Left chart is the configuration of equipment supporting default profile. Right chart is the configuration of equipment supporting telecom profile. From the result of interoperability test for the default profile, we found a difference in layers. So we used the same layers for the further experiments. Layer 2 Ethernet multicast is supported by a number of equipments. We detected problems that caused the failure of interoperability among profiles. The first problem is caused by different understanding of PTP header among equipments. And the second problem is the difference between transmission interval of sync message configured on equipment and actual transmission speed. And specifically, transmission is too fast to receive for some equipments. It results in connection failure in PTP. By feeding back these two problems, manufacturers have been asked to future improvement. About 30% of configuration of telecom profile was within the range of time accuracy regulated ITUT, the 8272/Y.1367. Two major problems. Number one, although protocol works, the lack of time accuracy between Grandmaster Clock, boundary clock, and slave could make the accuracy of Z.8272 low. We couldn't connect boundary clock with slave without adjustment of the protocol parameter to be out of standard. We reported the results of our experiments to the makers for improvement. And the detailed analysis of the stability for accurate synchronization is a matter of further consideration, but we found the accuracy show a periodical drift. I want to consider this as a challenge for the next year. Summary. Summing up, it is necessary to merge vendor PTP in order to achieve a high level of time synchronization for numerous nodes. SEIKO will keep experimenting with interoperability tests as shown it and promise to contribute multi-vendorization PTP. Reference link, and I heard this slide will be uploaded in website. If you are interested in PTP, please check it out. Lastly, we, SEIKO, will aim at the world's best grandmaster, pursuit of accurate time, expansion of the profile, expansion of the installation environment, interoperability as protocols, broadcast, SMPTE, etc. Adopting synchronization techniques other than PTP or NTP, we will contribute to the various industries. And thank you for your kind attention. And so, question, please email me. Thank you.
Thank you very much, Mr. Hasegawa.